drizzly morning, the second of these talks. Just remind, this is still all joint. That's not. And let me very briefly recall some of the notation from last time, but not all of it. So as previous lecture, let me fix G over QP, split connected inductive group containing this Borel at maximal torus. I also fix L not equal to P. I have all these coefficient categories that I recalled last time, which I don't want to notate. I have this Whittaker representation. And then, right, last time we discussed these two sort of naive functors. One from quasi-coherent sheaves on this stack towards one G, and one in the other direction. So this one was the one where you shriek extend this towards the whole stack, and you act by the spectral action on that. And then this functor is formally defined as its right adjoint. I should also say I was in error last time. A priori, this is not obviously Q colinear. It's just linear over dualizable objects here. Okay, but for the groups where we can say anything at all, it is Q colinear. So let me get to that in a second. So the goal is to prove this categorical local Langlands conjecture, which, recall, I stated in sort of a vague form and then a more refined form last time. So the refined form is that C psi restricts equivalence from compact sheaves on 1G towards coherent sheaves. And we don't anticipate being able to do this for all groups for the reasons I explained last time, but we at least hope that we can do this for groups where we have a solid understanding of classical local Langlands. So last time I was calling these well understood groups.
So, I'm sorry, but I missed the second half of your talk yesterday. There's no G check on the left?
This is notation, because okay, in general, we write a paper for quasi-split groups, right? And then the L group is strictly more data than the dual group. And I just prefer to have the notations sort of on the same footing. Writing Lucas G check in our setting would be misleading because you really need more than G check. And I just find I find L groups a little bit ugly, so I just prefer to write it like this. Yeah.
Okay, thanks.
Yeah, this is L-adically continuous sort of homomorphisms from the vague group of QP into the dual group of G in my setting. Yeah. Sorry, it's hiding the notational.
My fault for missing the second hour.
No worries. Okay. So that's the goal. And today I want to say a bit about the strategy and sort of how far we can get, in particular for GLN. And let me also remind you that last time I mentioned this one other input we need. So assuming this key working hypothesis, as I called it last time, that this functor C psi is compatible with Eisenstein series in some sense. Again, as I mentioned last time, for GL2, this is basically already been proved by someone. The general case is also work in progress. Okay. So let me start with a few little preliminary observations, and then I'll recall this strategy I stated at the very end, and then we'll try to examine the steps of the strategy in more detail. Okay. So some.
Can I just ask a question? So
yeah.
Sorry. So a priori, this statement is a construction rather than like a property.
Which statement?
This the CLLC. But sorry.
Categorical Langlands conjecture
yes.
is that this particular God-given functor gives you an equivalence of categories.
Oh, okay.
It's actually sharper than the classical set theoretic
Oh, okay.
Langlands conjecture. Yeah.
So there is a functor, and then the statement is that it's an equivalence.
That's exactly right. That's exactly right. Yeah, I mean, the functors are really handed to you by nature, and then this is some of the only functor that can do the job. Yeah. So the goal is really to prove that it actually is an equivalence. Yeah. Okay, so now for the rest of these talks, let me assume that G is well understood in the sense that I formulated last time. So roughly this means that we have some very good understanding of classical local Langlands for G and its inner forms, and that it's compatible with this Fargues-Scholze construction of L parameters. So let me mention some preliminary sort of consequences of this assumption, which already make things seem nice. Preliminary consequences. Of this condition. So first is that this A psi preserves compact objects. Remember, the stack of L parameters is not quasi-compact, so compact objects are not perfect complexes, they're perfect complexes quasi-compact support. And in general, it's still not obvious for general groups that this will send us towards compact sheaves on G, but here it does follow. It then is formally implied that this C psi is continuous, collinear. And the third point, which I want to dwell on a little bit because I didn't dig into this last time, and it'll be useful for other things later, is that the Fargues-Scholze map from irreducible smooth representations of this group G of QP towards what I was calling semi-simple L parameters last time. So these, let's think of as points, just closed points in this spectral Bernstein varieties, I called it last time. This map has finite fibers. And I want to give some recollection on where this map comes from in the language of the spectral action, because this will be useful to have in our pocket. Oops. So recall, last time we discussed the spectral action, which is some unmodal action of quasi-coherent sheaves on the stack of L parameters on sheaves on G. Right, now here's something formal you can do to get information of a lower sort of categorical level from this. I can pass to the induced map on endomorphisms of the identity functor. So what are endomorphisms of the identity functor? Here, it's just global sections of the structure sheaf on this stack. Which you could write in several different ways. You could also think of it as functions on this course moduli by definition. So this will formally obtain a ring homomorphism towards endomorphisms of the identity functor here, right? And this is a very general construction, right? By definition, this is just the center of this category. Okay, maybe I denote with a big capital frac Z. Oops, sheets. G. Okay. And now remember, we have this distinguished point b equals 1 in Bun-G, and Schriek push forward from that point embeds representations of G of QP sort of fully faithfully into sheaves on Bun-G. And if you have a fully faithful embedding of categories, you get a map the other way on their centers. So this will induce a map towards the center. Well, I just write it like this.
What do you mean by center?
The ring of endomorphisms of the identity functor.
So you consider D of G as tensor category.
I don't think I need tensor structure.
No, but
It's like the Bernstein center. But
it's a Bernstein.
that's this type of construction.
Maybe one.
Yeah, compatible systems of endomorphisms of all objects in the category at once.
So it's a Bernstein center, but taking in account if we're even not with the usual category, but with the
Yeah, that's right. But here I actually only care about what's happening at the one categorical level. So, yeah. Okay. And so this is just the usual Bernstein center. Sorry, I should notate this is sort of induced by this map I1 over Schriek. Okay. And in particular, if you have an irreducible smooth representation pi, you get a maximal ideal associated with it, right? By definition, irreducible representations will give you sort of points in the Bernstein variety which translate into maximal ideals in this ring, right? And if you compose this, you'll see that this composition produces a maximal ideal in this ring, which gives you a closed point in this space of semi-simple L parameters, and that's exactly the Fargues-Scholze parameter. Okay?
Sorry.
Yeah.
So how the morphism of the identity functor acted on the Bun-G?
It's confusing. So the identity functor here, right? I'm doing a trick. I'm writing that the identity functor here is what you get by letting the structure sheaf act, right? Because it's a monodal action, so the modal unit has to act by the identity, right? But then endomorphisms of this will give me endomorphisms of this.
So you take the morphism of the identity functor, and
Yeah.
then you look how it acts on the structure sheaf, and that gives you the action.
That gives you the map, right? But of course the subtle information is that there is an action like this in the first place, right?
Sorry, wait, so right, you mean endomorphisms of the unit object in Categorical sub G gives you endomorphisms of the identity functor in D of Bun-G?
Yes.
Okay.
I think that's right. I think there's different ways to sort of unwind this, but yes.
What is the match from the usual Bernstein center to QL bar? First of all, I don't see the notation. It's something.
Sort of maximal ideal. Maybe I should say quotient by maximal ideal.
But which maximal?
Right, so the Bernstein center, right, this is also, you can also think of this as the ring of functions on this Bernstein variety, right, this variety of sort of supercustomal supports. And pi,
we
really-
started with some pi.
Yeah.
And this.
that's right.
This is what.
Yeah, a better, more geometric way to say it is that this map of rings, so equivalent, is that you get a map of rings, a map of schemes. Which is sort of dual to the induced map on rings here. Okay, and from that point of view, I think it's extremely transparent, right? Points here correspond to supercustomal supports. Of course, any pi has supercustomal support, and then points here correspond to semi-simple L parameters.
I have a general request.
Of course.
So, my understanding in the talk, in your proof or sketch the proof, a substantial part consists of, either active nonsense or just formal corollaries of the theory developed by Fargues-Scholze. However, probably there will be some critical places where, and also you will use, at some point you have, yes, and when you, this kind of arguments, my understanding is that here you are, this is a kind of abstract nonsense.
Yes, indeed, indeed.
and it's probably easy to understand, but not at that speed. So when you explain the shift nonsense, I basically have to fall asleep or to relax.
Okay.
I write it down, but I simply cannot understand abstract nonsense at that speed, and
Okay.
at a smaller, lower speed would be probably unacceptable for me.
Well, maybe let me switch from abstract nonsense to.
At some points, you have to wake us up.
Okay.
You have to tell us that here you are doing something which is not abstract nonsense.
Okay, let me try to focus it on those aspects of the story then, things that are not abstract nonsense.
Yes, I'm not saying you have to explain some abstract nonsense, but you have to wake us up.
We're not completely allergic to it, but it can be.
Yes, but at some point you have to wake us up.
Like melatonin or something. Okay, sounds good. Okay, so now let me come back to this strategy I stated last time, and then let me try to focus really on what the new ideas are with a minimum of abstract, well, unmotivated abstract nonsense. Okay, so the strategy I stated last time. So the first is to construct this functor L psi, right like this. So this is supposed to be the sort of true Langlands functor, so this is denoted L psi, and this is supposed to lift our given functor C psi, which has target Q code, along this projection map from incoherent sheaves towards quasi-coherent sheaves. Okay, so construct sort of lift. Let me call this a lifting. I sort of think of it as some enhancement of this to something where the target is now correct. And we want this to have good properties, so which is continuous with continuous right adjoint. And the right adjoint will play a key role in the story, and I denoted by R psi. Okay. Now asking for it to be continuous already implies that it has a right adjoint by the adjoint functor theorem. And then asking further that the right adjoint be continuous is equivalent to asking that this lifting preserves compact objects, right? And compact objects here are just co, and co here maps sort of isomorphically to the natural copy of co here. And so if you stare at the structures here, you realize that this is equivalent to showing that C psi restrict its domain to compact sheaves as image in code, which Professor Felix asked about last time. Okay. So now let me try to explain how we do this in broad strokes. Oh, sorry, I should label this as part 1. Apologies. What is the idea here? So the idea here is that we've given ourselves some leverage because we're assuming this functor C psi is compatible with parabolic induction in some sense. And so you can hope to do some kind of induction on levies using this. And for this you need to know something about how the category of sheaves on Bungie decomposes into, say, some Hospital part and some Eisenstein part. Okay, so this is extremely in parallel with a construction due to Drinfeld and Gates theory, I believe, in D-modular geometric Langlands. And here it was proved in this recent paper of myself and Lucas Mann. Excuse me, Peter Schulze. Too many names involved. Okay. so as in Linus's talk last week, we have this good theory now of constant term functors and Eisenstein functors on Bungie. So one thing that we can prove using them in particular is that if we define the Eisenstein part of Bungie to be the subcategory generated by the images of these Eisenstein functors for all proper parabolics. And define the cuspidal part to be the common kernel of their right adjoints, which are these functors of constant term. Okay. So in ordinary geometric Langlands, these two subcategories would form a semi-orthogonal decomposition of sheaves on Bungie, right? And morally, the reason that they're semi-orthogonal and not truly orthogonal is that on the locus side, irreducible local systems and reducible local systems talk to each other, right? Irreducible local systems are open and dense, but they can degenerate sort of to reducible ones, right? Here, the story is a little bit different. In the stack of L parameters, the irreducible locus is open and closed, okay? And what that translates to morally on this side is that these two categories actually form an orthogonal decomposition. So this is canonically the direct sum of these two subcategories. And there's absolutely no problems between either of these two subcategories in either direction. Okay, so this is helpful because we also know that these Eisenstein series have good finiteness properties. They preserve compact objects. So this will be compactly generated by Eisenstein series applied to compact stuff. Okay, and so then on the Eisenstein part, we can use an induction because we're assuming something about the compatibility of C psi. So how would this go? So let's suppose that I want to prove that C psi applied to something of the form ISP shriek A is covariant, okay? Where A is a compact sheaf on Bun M for some M. So what can I do? Well, I'm giving myself some a priori compatibility between these two functors, right? This is this key working hypothesis, so I can rewrite this as a spectral Eisenstein series composed with the version of this C functor, but for the Levy M of A, right? So this follows from this key assumption. And now this, maybe let me even use some color. So this is in co of the stack of parameters for M by induction, say on the semi-simple rank, if you like. And then this functor, spectral Eisenstein series, this preserves co, right? Because the structure of the spectral Eisenstein series is that you do a sort of quasi-smooth pullback, and that preserves co, and then you do a proper push forward, and proper push forward also preserves coherent sheaves. Okay? So that's how you do the Eisenstein part. So the cuspidal part you can further decompose. Sorry, I seem to be moving right to left. But that's not really a big flip. as I mentioned a moment ago, the stack of L parameters, the locus where the parameter is irreducible is both open and closed, and likewise for the locus where the parameter is reducible. Okay. And so this gives me some idempotence in the ring of functions on this space of semi-simple L parameters, right? As I mentioned over on this board, this is the only piece of abstract nonsense I need for now. We do have a ring homomorphism from that ring towards the center of this category of sheaves on Bun G, right? And of course, this is a ring homomorphism, so we'll preserve idempotence. So these idempotence will give me another direct sum decomposition of sheaves on Bun G, right?
So in other words, you just take the cuspidal part and observe that it's more or less, well, almost a discrete set. Maybe at least in the case of GLN.
Do you mean on this L parameter side?
Well,
That's right. The cuspidal part, this stack is extremely concrete and simple. For a semi-simple group, it's sort of a disjoint union of points modulo finite groups.
Well, it is concrete for GL2,
Yeah.
and it's simple in some sense,
Yeah.
but not in others, because
Indeed.
After all, you are talking about reducible representations of the Galois group, of the inertia group, let's say, with values in GLN, and then it's not, it's a pretty delicate object, but it's simple in the sense that, that as you say,
enumerating, really writing it down explicitly is
more or
subtle.
less a discrete set.
Exactly.
At least for GLN and maybe up to center.
Exactly. And that will play a strategic role in what I'm about to say. Exactly. So these idempotents give me another decomposition of this sheaf category. And just to note it sort of an obvious way. Oops. Now we have these two these two orthogonal decompositions of the category. And what is straightforward to see is that there are certain one-way inclusions. So anything in the Eisenstein subcategory has reducible L parameter, and conversely, or orthogonally if you like, anything with irreducible L parameter is customable. Okay.
And in some sense, we're still doing abstract nonsense. We don't.
Indeed. Very soft abstract nonsense. I haven't taken advantage of this well understoodness yet in this argument, but I will in a moment. So conjecture. So this was formulated in this paper of Linus and myself and Scholze, and also independently by Yuta Takaya. So the conjecture is that these inclusions, maybe I should write this just ecology, are equalities for all groups. And in fact, they're quasi-split. G, if you set the theory correctly. Okay. So vanishing of all constant term functors should imply that the representation has irreducible L parameter, okay? So this is strictly stronger than somehow being supercuspidal, right? Because of these funny mixed L packets, right? Where you have supercuspidals with non-supercuspidal parameter. Okay? That's a proposition. This is true. Well understood. Okay, and this is the essential point where it is not abstract nonsense. So this uses the endoscopic character identity. Right? And what you're faced with is a slightly funny thing in proving this, right? You have to prove that this inclusion is an equality, or equivalently that this inclusion is an equality, right? And what this amounts to in the end is proving that if you have a supercuspidal representation of GB for some basic B, whose L parameter is not irreducible, then, well, this is an orthogonal decomposition, so it's enough to see that it has a map, a non-zero map from something in this subcategory, right? And this you can do by some tricks, using the fact that somewhere else in its L packet, there's a non-supercuspidal representation. Okay, so.
Okay, so this is not abstract nonsense.
Not abstract nonsense.
But what goes into what kind of mathematics goes into the proof? Is it the theory, the conventional theory of representations of p-adic groups, or is it the Fargues-Scholze theory, or a combination of both?
It's a combination, and the other key input is this paper I wrote with Jared Weinstein and Tasha Paletha a few years ago, which basically tells you how to compute Harish-Chandra characters of Heck operators applied to certain kinds of sheaves on Bungie. Should I use it as character identities plus the paper I wrote with Jared and Tasha? Okay, but yeah, the moral takeaway is that this is not abstract nonsense. If one could prove this conjecture for a general group, I would be extremely amazed. That would be really, really, really interesting. Okay, and now we're done with this step, because as Professor Grunfeld was saying, this stack of irreducible parameters is somehow down to earth in certain ways. And that makes it fairly easy to prove that on this category, C psi has the right finiteness properties. And now you're done, because you know there's nothing here that didn't come from here. So it's easy to show C psi. And you have, of course, compact objects. This lands in code. And so by the proposition, let's say we obtained all sheaves. And this can be done for any group. This doesn't require this well-understoodness. But in general, right, the stuff in this irreducible idempotent projection plus the Eisenstein stuff may not be the whole category. That's what you're contending with here. If you don't know that that left-hand inclusion is an equality. Okay, so that's the point. Okay, that's the sketch of step 1 in this strategy. So now we come to step 2.
So, what is the precise meaning of the word we obtained all sheaves?
Let me make this more precise. So all this category, right? A priori, you can decompose it as the Eisenstein part, direct sum is irreducible idempotent applied to the whole category, right? And in general, there may be some extra stuff because we don't know that that left-hand inclusion is an equality, right? But according to this proposition, in fact, for well-understood G, these two subcategories span the whole category. Sorry, that's what I meant when I said we obtained all sheaves. And here C psi is straightforward to understand, and here we understood it inductively. Okay. Say again by proposition above. This is true. Which gives the result. Sorry, now the rhetoric on the board makes a little more sense. Okay. So that's step 1. And so now we have access to this right adjoint, which is continuous. And because it's continuous, it's also collinear, and there's other nice features that it has. It's not at all obvious that it preserves compact objects. So this is part 2. also want to formally point something out, although I may not write it on the board. We assumed that the C psi had some Eisenstein compatibility. It's formal nonsense to upgrade that to a compatibility of this L, this lifted true functor with Eisenstein series. This will formally pass to a statement about the right adjoints, because the right adjoint to Eisenstein series is constant term. And so you do know one more thing about this R, sorry, which is that it has some compatibility with constant terms. Okay, and so I will use that in a moment. But for now, let me state something general. So for this, we use the following. Result, so proposition. So, and here I really need to be well understood. So this proposition is a criterion for a sheaf on Bun G to be compact. In a moment, we will apply this criterion to this right adjoint functor. And this is the case if only if three things hold. One, it's kind of obvious. This is that A is obviously necessary, it has compact support. Let's say quasi-compact. Support. The second one is a spectral version of that. So, as I mentioned earlier, right, we have this map from functions on this variety of semi-simple L parameters towards endomorphisms of the identity. In particular, they'll act on any object in this sheaf category. And so you can talk about the support of a sheaf in this variety of semi-simple L parameters. So part two of this is that this support is quasi-compact. Which again is not automatic because this has infinitely many connected components. And the third part is that for all compact B in the sheaf category, if I compute R harms from B to A. So a priori this is just some complex, but again, I'm going to repeatedly use the fact that I have this sort of spectral, this map from the functions on this variety towards the center of the category. Right? So this is a complex whose cohomology groups admit an action of a ring of functions here. And the third part here is that this is a bounded complex. But finitely generated. XG spec. Watch this.
So the question is written that R home of ZA is, and then what?
A bounded complex.
Bounded, yeah.
And I don't want to really say anything about the proof of this proposition. It's not very difficult. It just uses some Bernstein theory and sort of the explicit set of compact generators that Fargues-Scholze tell you have.
Sorry, that's the same thing as being pure? Is that right?
Second.
Is that the same thing as being a co of?
Be careful, that Arham is on the automorphic side,
Okay.
right? But it upgrades a little bit, right? You get this action of rings on the course functions on the course moduli. I'm not saying it's an object in like Hugo, of the stack L parameters.
Oh.
Yeah. But it does this string of words does make sense. This is again via this Fargues-Scholze map, via this honey map. Yeah. So we want to apply this criterion. To a sheaf. Let's say like this, two objects. I take this right adjoint functor and I apply it to some coherent sheaf on the stack of L parameters. This is my name, just to be clear. So which parts of this are easy? 2 is clear. Because part of the definition of being incoherent is actually that you do a quasi-compact support, and by the very nature of this functor, the support of this thing in this space of course in this course moduli will just be the support of this in this stack of L parameters projected down. Okay? So somehow it's very easy to check too, just by the way the sheaf was cooked up. And 1 and 3, however, are not obvious. But you can get some clue for what kind of information you might need, say, to verify 3. So 3. So let's look at 3 for a moment. So for 3. Let's just do something a little bit formal. If I have a compact sheaf on G, and I want to compute hums towards this right adjoint. Okay, well, it's hums towards a right adjoint, so I can replace it with the left adjoint applied to the other factor. Right, so this is certainly a valid equation. And what do you know here? So this is in co by assumption, right? And B was compact, and so by step 1 in this whole strategy, this functor will send B towards something that's also coherent complex. Okay. And also, if you believe L is an equivalence, you can sort of see that any coherent sheaf can be realized in this first slot, and any coherent sheaf certainly can be here for the argument. So now you're reduced to the following thing, which is a theorem. So theorem. So now use following theorem. So for all, let's say F and G, let's get rid of coherent sheaves on the stack of L parameters. R home is a bounded complex. Yeah, whose cohomologies are finitely general.
Is it the internal or
No, it's the external. So it's derived global sections of the internal are home.
yes, I'm a little bit confused about this. So part G is an infinite disjoint union. And coherent means that its support is finite.
Yeah, my notation may be slightly non-standard. The most precise thing that you might write here would be like D bounded quasi-compact support co.
So co includes this condition that it lives on finite domain.
Indeed.
Because otherwise, so it's not a local. This is usually co being coherent is a local condition, but here.
Yeah, I realize this is slightly non-standard, but the reason
it's okay, but anyway, it's you explain.
I do with this notation. It is true that int code is int of code for this stack, which is why this is, I think, reasonable notation. Right, so this is external. And this theorem is a little bit of a miracle because this stack has singularities, right? If this were a variety with singularities, there would be absolutely no chance that this could be true, right? X between random coherent sheaves on a singular thing, right? Sort of drift off to the right kind of arbitrarily far. So here the stackiness is somehow canceling out with the singularities. Okay.
last time you explained that the stack of parameters is, I think, pretty nice. It's,
Yeah.
LCI, for instance.
That's right.
But LCI wouldn't be enough. It would probably smoothness would be enough for this.
Right. But if it were, I mean, this theorem would fail for any singular variety.
Yes.
Right.
But here you have a singular stack.
Yeah.
And the stackiness kills.
That's right. That's right. So we discovered this by example, actually. So this was discovered experimentally by playing with a local model for some piece of the stack for GL2. So stack. So this is sort of a local model for a piece of actually one of these parameter stacks. So you take polynomials, two variables, kill xy. So this is just a union of two lines meeting at a point. But then there's a GM action, and T GM acts on this pair by doing nothing to x and translating y by t squared. So it's somehow the weight 2 action on one of these two lines and a trivial action on the other, but the lines meet. Okay, so this is singular, and you can check by hand that this satisfies the conclusion of this theorem. Okay, so in fact, this is a local model for the only singularity of the stack when the group is PGL2. And so we discovered this theorem sort of by just noticing that it was kind of true by hand in this example. Okay. So this theorem requires maybe the most delicate analysis anywhere in the project. So the proof of the theorem uses several ingredients. So one of them is due to Kaya. This is a very nice fact that if you want to understand coherent sheaves on this stack, you can inductively understand it in terms of proper levies. Well, let me say it like this. This is generated under finite colimits and retracts by applying spectral Eisenstein functors to perfect complexes on parameter stacks of levies. And I do allow P equals G. Okay. So actually you can get a set of compact generators by taking these sort of spectral parabolic inductions of perfect complexes, or even of certain vector bundles if you stare more carefully at the argument that Takeda gives. And so this tells you that in this theorem, you can, if you look a little bit closely at the way that these sheaves sit inside here, it actually reduces you to the case where either both f and g are vector bundles, in which case the theorem is easy, or you can actually assume that they're both in the image of some Eisenstein functors. And so then by some adjointness, you can replace one of the Eisenstein series with a constant term, and now you're faced with a question of whether constant term functors have any good finiteness properties. So this is maybe the key technical thing. So yeah, let me actually put this on its own board. And then after this, maybe we take a 5-minute break. So let me actually a little bit carefully recall the diagram that is involved in the definition of these spectral Eisenstein series. Constant term functors. So this I guess I call spec. Well, let's just call it Q and P. Okay. So then this I is P spec in this INDCO formalism, it's what I guess case where there's no P lower star INDCO Q upper shriek INDCO. But this map Q is extremely nice. It's quasi-smooth of relative dimension 0 with trivial relative dualizing sheaf. And so in fact, this upper shriek is just also an upper star. Okay. And so this has a right adjoint. CTP spec. Because this map P is proper, its right adjoint, the right adjoint of this is P upper shriek INDCO. And then because I can rewrite this as this has a right adjoint which is Q lower star. Okay. And now I want to observe something. This maps towards incoherent sheaves on the stack for this Levy subgroup. And now recall last time, these parameter stacks are global quotient stacks by the dual group, right? And in particular, the center of the group will give rise to a canonical isotypic decomposition of coherent sheaves or incoherent sheaves on these quotient stacks, right? This is a very general thing. If you have a quotient stack and a central subgroup of the thing you're quotienting by, characters of that central subgroup will give you a grading on coherent sheaves, right? So this will actually break up as a product category over all chi in the character group at the center of M hat, say int co RM chi graded part, right? And this tells you that this, excuse me, spectre, this functor is canonically product over chi's of obvious graded parts. No, theorem. Which is a little bit surprising. Maybe already the first part is surprising. If you look how this functor is defined. These individual graded pieces preserve co inside INDCO. This is not obvious from the definition because upper INDCO, upper shriek along that first map doesn't preserve co, and lower star along the second map doesn't either. So it's built from functors that both destroy coherence. And indeed, if you don't restrict to a graded piece, it does destroy coherence. But by some kind of miracle, the individual graded pieces do. Okay. And so this, together with some induction on levies, is already enough to prove this theorem here. And so that at that point, you're done with sort of 2 of the 3 parts of this compactness criterion. And for the third part of it, we need a little bit more control over these than just this soft statement. But let me not state this totally precisely in this talk. I say it for most in a very precise sense. Let me say this for F and co RG fixed. And most chi, which I can make precise later or maybe in the question and answer session if someone wants to really know. And most chi, where most depends on F. This functor applied to F is identical to 0. Maybe just to be a little less mysterious, let me say for most chi in a certain cone. And if you unwind carefully what I mean by most in the second part of this theorem, you can actually deduce the first of the conditions in this compactness criterion, which is the only missing one. Okay. And yeah, I think this is sort of a good place to stop because
I have
for the
a
break.
question.
Yeah, please.
So you formulated this theorem and you said that its proof is the most delicate part of your story. Now, here is a question.
Yeah.
In this theorem, do you assume that G is well understood?
No.
No. So unlike the other parts of your proof, this is true for all G.
That's right. So these results I'm saying here on the spectral side, just this theorem and this theorem, these hold for these are true for any quasi-split group. Yeah. Somehow a lot of the preparation work in our paper is laying these sort of foundations on the spectral side, these finiteness theorems for constant term functors, and some sort of control over which graded pieces of them actually vanish identically.
So do we have a break now?
Is that okay with you?
Yes.
I think this is a good breaking point before we get to the other. So as I said, this strategy is sort of in 4 parts. This concludes my summary of the first 2 parts. So far, everything is valid for any of these well understood groups. And now we'll start to get a little bit more specific in terms of which groups we have a full understanding for. So this third part of the strategy is to try to show that this right adjoint functor is fully faithful. Okay. And this will actually break down into several intermediate things. And one of them will involve a new functor, which is maybe the main new idea in this whole project. This is how this project started, actually, when we realized this thing I haven't told you yet was a part of the story. And so what is the idea here? So let's see. Some steps. So the first is one that I mentioned last time, which is that we do have one functor in the picture, which is somehow the most concrete one, which is this functor a psi that goes from quasi-coherent sheaves on the stack towards sheaves on 1G. Right, this is really the one we start with in my philosophy. You just act spectrally on this God-given Whittaker sheaf. And you could ask, because it is part of the conjecture, right, that this should be fully faithful. In fact, you can sort of check that the conjecture, if the conjecture holds, this must be fully faithful. Right, so this will enter the story at some point. And this actually has a kind of concrete meaning, because this is, in our setting, this is Q-collinear with a Q-collinear continuous right adjoint. And so you just need to know that the composition of the 2 adjoints is the identity, right? But the composition of the adjoints is Q-collinear. And so now you're reduced to checking that the composition of the adjoints on the structure sheaf is the structure sheaf, right? And so this is a somewhat concrete thing, and it holds if and only if, when you apply C side to this Whittaker sheaf, you get the structure sheaf. Okay, so that's completely formal. Nothing really interesting happened there. But then we will show that for some other functor I haven't defined yet, if a psi is fully faithful, then this functor that I call t psi is fully faithful. And this will imply in turn that r psi is fully faithful. And so this is okay for all understood G. And then the next part is for GLN, we will show. That this can be computed and that it indeed gives what we expect. And this I haven't spoken of yet. Okay. So this is some new strange player in the story. Before I expose you to a little bit of abstract nonsense, let me say what the point of this functor t is. Okay, this functor A is defined on all of QCO, but QCO, the way QCO sits inside IntCo is a little bit unhelpful, right? It's not obvious how to extend the domain of A to sort of something on all of QCO. This functor T will actually be defined on genuine coherent sheaves inside IntCo, on some small part of it, but we will actually have an explicit formula for this functor in terms of A, okay? So this is maybe the most surprising part of the story. And so let me develop a little bit of nonsense theory, and then we can talk about what's happening in that chain of implications, okay? And so what is this nonsense theory motivated by? So it's motivated by taking seriously the idea that we should examine sort of the different finiteness conditions on both sides. Right, so if we believe in this categorical conjecture, then compact sheaves on bun G should match with coherent sheaves on the stack of all parameters. Right? But there's another finiteness condition you can impose here, which came up in Linus's talk last week. Right, we can talk about these ULA sheaves. Right, so these morally, these are like sort of finitely generated representations, and these are morally like admissible representations, right? And so what is this? So this is a proposition that I'm writing here, not a theorem. These are A, such that for all compact B, again, the external arhams from B towards A is a perfect complex of vector spaces. Yeah.
It's a description of the what ULA means.
That's right. That's right. It's not the definition, but it's
not a description of the guy who corresponds to the. So you wrote a double arrow, but you didn't write what.
Yeah. So we're going to fill that in a second. But this is a proposition in Fargues-Scholze. This is some abstract nonsense condition, and for Bungie, it boils down exactly to this. Okay, but now we have some guidance for how to translate that, because compact B's translate towards coherent things on the other side. And so now let's just make a definition. So I call these admissible incoherent sheaves. So these are exactly the objects F in stack parameters. So for all G, co. G to F. It's a perfect complex of vector spaces. Okay, so if you believe in the categorical conjecture, right, you're forced to consider this category on the right if you ask yourself what category should match with ULA sheaves, right? Exactly because coherent G's will translate into compact B's, right? And let me do one more thing. You can intersect these two conditions. This will give you some extremely small category. So this I give special notation to. So I call these finite sheaves, and there's a good reason for this. So these are exactly the sheaves such that the sum over all B and all N of the length of the nth cohomology sheaf of the stalk at B is finite. So they're finite length in the strongest sense. Okay? They can be gotten from irreducible representations of these groups GB on strata in finitely many steps. And so, of course, formally this will intersect, this will match with like admissible intersected with coherent on this stack of all parameters. Okay. I haven't done much so far. I've just sort of contemplated some additional categories. this down prematurely. So there's one more aspect of this story, which is important for this new functor, is that there's a duality on these ULA sheaves. This is like varieties duality, so it's just internal hom towards the dualizing sheaf, which turns out to be non-canonically just the constant sheaf. And you can ask, what does this duality match on the other side, right? So note. So this definition of admissible whatever, so this makes sense. For any UCA derived stack. In the sense of this paper of Drinfeld and Gatesford, called, I think, some finiteness theories for algebraic stacks. Simply because in this case, int co is compactly generated, so you get a reasonable condition by asking sort of which sheaves, when you hom from co, do you get a perfect complex of vector spaces over the base field. Okay. Yeah.
Just don't, at some point, on the one hand, I stopped understanding what was going on.
Okay.
On the other hand, you woke me up by mentioning my name.
Yes.
Can you say again what? So you said that there is something similar in our paper on finiteness. You mean it's about compact generation?
Yeah, that's right. That's right. So because when int co is compactly generated, this is a reasonable condition that you can ask about, like which sheaves get satisfy this alternative finiteness property that when you do R-homs from co, you get a perfect complex.
No, so the paper you are referring to is not about compact generation of D of Banchi. It's a paper on kind of general theory of D model.
Right, but it was very helpful for me.
No, I understand, but now I want to understand.
Okay, let me say something that will wake you up and help you see where this is going. I want to write down a spectral analog of the functor pseudo-identity star. And I want to prove that it takes image in tempered D modules. But in some spectral
Yes, and now
setting.
the words pseudo-identity refer to some papers by Categorical and
That's right.
Categorical.
That's right. So there's two dualities in this theory on Bungie. There was this Bernstein-Zelowitsky functor, which is the exact analog of the miraculous duality, which is sometimes also called pseudo-identity shriek. And there's also a Verdier duality on Bungie, which is the exact analog of the pseudo-identity star, right? And the question I want to address now, which is actually important for our work, is what is the spectral analog of pseudo-identity star? So this turns out to make sense in some more generality. So this category of indivisible sheaves. So there is a duality tree. So definition. Let's say a UCA derived stack X. So I write D admissible. So this is some endofunctor of this category. So this is defined by asking that R homs towards it. Given as the dual of the int co-global sections of the tensor product at F and G. So this is for all F and G. And now the reason this makes sense as a definition is that if you stare at what I wrote down here, everything up until this step commutes with colimits in both variables, but then this final step converts colimits into limits, right? And so if I fix G, then this is a sort of functor which, it's a contravariant colimit preserving functor, so it's representable, right? And by definition, this is the representing object, okay? By the adjoint functor theory, this at least exists. In general, let me say this is an extremely weird operation. It destroys coherence.
Sorry, and is it V or check? What is this?
This was a check that got over exaggerated. Sort of naive QL dual. This is just a complex QL vector spaces. Take naive dual. So proposition. So this induces perfect duality on the subcategory of admissible sheaves, such that on this subcategory you can satisfies bi-duality. You compose it itself twice to get the identity. It even detects admissibility. In the sense that if you apply this to a random sheaf and what comes out lies in this subcategory, then what you started with already lies in this subcategory. And there's also a nice formula which is a very helpful way to think about this functor. So this archon, which already appeared on the board, can actually be expressed in a different way by instead computing archons, where instead of doing this strange dual on the second factor, you do growth and decay duality on the first factor, and then you dualize the whole thing. So I call this duality exchange formula. So actually, given the third one of these, the third part of this proposition, which is actually a straightforward consequence of the definition and a formula in the Strinfeld-Gates-Squared paper, the other two parts are actually somewhat straightforward, simply because this sort of induces an anti-equivalence on Co, and then this preserves and reflects perfect complexes of QL bar vector spaces. So once I've told you these three things, the third one actually implies the other two. But this functor satisfies a more serious property. Yes.
So you de-admissible, and then in the last term there is GS. What is GS?
This is good old growth and decay duality.
Ah. So the usual one.
The usual one, exactly. And in our case, this is especially nice because the stack of L parameters has trivial dualizing sheaf. That's right. So it expresses this strange duality in terms of this more comfortable duality, but at the expense of this one additional funny step here. Okay. This functor, however, satisfies a much weirder property, and this is what I was promising you a moment ago. This is the analog of the fact that pseudo-identity star has image and tempered D-modules. Okay? So this theorem can be expressed more generally. So for any QCA X, which is both perfect in the sense that it has enough perfect complexes, QCO is compactly generated by perf. And I also need to assume a little bit about the singularities. So I
What
need
is QCA?
a quasi-compact with affine diagonal.
Ah,
Right.
maybe it's
I can
from-
just
I
borrow
think
it from your
our
paper. I borrow it
yes.
from your paper.
Yes, but even I forgot this notation, and I'm not sure.
It just means, you know,
QCA means quasi-compact with a fine diagonal.
yeah, that means that it's humane in some sense.
Yes.
And I need to assume, moreover, that it's perfect and Ornstein. Okay. And for all F,
What is perfect here?
so by this I mean that QCO is imperfect by definition. So it means that QCO is compactly generated.
So it has nothing to do with perfect rings and
No.
with perfectness from the other parts of it.
Yeah, it means there are enough perfect complexes. I think I borrowed this term from this paper of NC Francis and Adler, I think, 2008. Consider this condition in some detail. Okay, so then the conclusion is a little bit funny. Is that if I take a random coherent sheaf and I apply this duality, this will destroy coherence in general, but what it does actually do is it sort of temporizes the sheaf. So this is in the image of this funny functor xc. So remember that xc sort of embeds QCO into info. And then this other functor, capital C, projects it back, and the composite is the identity. Okay. So, although it destroys coherence, it somehow temporizes the sheaf. And this is the analog I was promising you.
Temporizes, so makes it tempered.
That's right. So let me just say this on the word in words. So this is the analog of, and I put this in quotes because it may not be helpful to the whole audience. It may be helpful to some people. This is if I understand correctly, this is a theorem of Dario Peralta in the setting of classical geometric magnets. Okay. Okay, now you're probably wondering what is the point of all this? So let me conjure up a functor out of nowhere, but I will only be able to conjure it using what I just told you, and then I will explain the point. Okay. But I need one more small observation before I conjure up this functor, which is that this overlap. So I told you that this functor induces a duality on admissible sheaves, and on coherent sheaves, it does something even more miraculous. It sort of temporizes them, and so you may not be surprised that I'm going to consider it sort of on the overlap of these two categories. So that's the stuff that's admissible and coherent. And on the stack of L parameters, you can prove that this has a very concrete characterization. And this is a theorem. Not totally obvious. So I write co Fargues fin. And these are exactly the coherent F, which are supported set theoretically on finitely many fibers of the coarse moduli map. So recall we have this map from the stack of all L parameters towards this coarse moduli space of semi-simple L parameters, right? If you have a coherent sheaf upstairs, you can impose this extremely restrictive condition that set theoretically it just live on finitely many fibers of these. Okay. This is the exact analog of coherent sheaves on the stack of local systems with restricted variation in classical geometric Langlands. Okay. So this, even though I put it in 2-point font, is actually kind of important. This overlap is exactly this concrete category. So now I can define for you this functor T that I promised earlier. And this definition makes sense for any group, but we can only say anything about it for groups where we know something. So this functor will have a rather small domain. domain exactly this overlap, so these sheaves that are supposed to match with finite length sheaves on the automorphic side in some sense. And we'll have target all of Bungie, sheaves on Bungie. And the recipe, take advantage of everything I wrote, but it will look a little funny. So I take my f, I apply not quite this admissible tool, but some twist of it. Some technical reason the Chevrolet involution appears. This is a twist by the Chevrolet involution. Okay. And now, this is a particular coherent sheaf, and the stack of L parameters satisfies all the conditions of this theorem. And so this is now in the image of this fully faithful functor after this first duality has been applied. Okay. And so for pedantry, let me write it now. Sort of C inverse. This makes good sense by the theorem I put on the board over there. And so this is in Q code. It may not be perfect, it may be enormous in some sense, but it is a quasi-coherent sheaf. And so it makes sense to apply this functor A to it. So now you have a sheaf on Bungie. And finally, you take its variety tool.
So it's A corresponding to the inverse of C, or what is it?
That's right. A corresponding, A subscript psi inverse. Make it like better typesetting. Okay, so this functor looks crazy. It's not at all clear why. Why should I write this random combination of things down? Okay. So theorem, and again, I want to emphasize this definition makes sense for any group. Okay, I didn't actually use anything except the sort of temporization property of this here in the definition. Okay, so theorem. Geez, well understood. This T psi actually gives you a formula for this abstractly defined right adjoint on this category of smallish sheaves. So I want to emphasize again how sort of useful this might be if you think about it. The way we defined this was in several steps, right? We started with A, which is given to us in some explicit way. We passed to a right adjoint, which we don't understand very well. Then we carefully lifted that along some other functor to get L, and then we passed to another right adjoint, right? So we're sort of many steps removed from the spectral action, right? And somehow this feels like a very inexplicit functor at this point. But on the other hand, what am I telling you here? I'm telling you if you restrict this to this category, at least, you can actually write down a formula for it. And that formula involves, up to some dualities, the most naive of all the functors. It involves just the spectral action on the Whittaker sheaf. Okay? Right, so A stands for action, C stands for coefficient, T stands for either tempered, because this has this magic temporizing property, or it stands for twisted, because you take this A and kind of twist it by too many different dualities. Okay. Yes, I still have some stuff on the board that I can point to. Maybe I don't actually want to go into this in super detail, but now that I have this definition, let me come back to this logical chain that I had over here. We have this spectral action, which is the most explicit functor. And then it turns out one can prove that if that is fully faithful, then also this T psi is fully faithful. Okay, and really, maybe I'm secretly inverting psi somewhere in that, but that doesn't really matter. So let's say idea it's not fully faithful. That's T psi. The idea is to simply stare at this composition and think to yourself, what do I know about the pieces that build it? Okay. So I already told you something about this admissible duality. It actually gives you a perfect involutive duality on this category here. Right? And the sheaves that we're starting with live in this overlap of this with co, right? So on that first step, you have a fully faithful operation, right? The first duality loses no information. This A side we're assuming is fully faithful, right? And then the only possible problem is this final variety dual on Bungie, right? So, say this and A side preserved are fully faithful. The only problem is this final third. Okay. What do you know? It is formal that the image of this T side sits inside UL issues. Okay, this follows from this comparison of this functor R. And this composite ended with a Verdier dual. And it turns out in this situation, Verdier duality it both preserves UL-ness and it actually also detects it. Okay? This preserves and detects UL-ness. Okay? Which means that already at the first two steps, when we did the funny temporizing dual and the spectral action, we must have gotten a UL issued. And then we win because this is fully faithful on UL issues. So the final step there is also fully faithful. Let me just point at it one more time in words now that I have brought this board down. This was admissible in particular. So this is fully faithful on the category where this lives. Then we're assuming this is fully faithful. So these two steps are. And we know the final outcome is ULA, which means we must have already been ULA after these first two steps. And this is fully faithful on UL issues. So that's how you see that this composite is ULA. I mean, it's fully faithful. Okay, so that's a sketch at least of this step. And this step, I don't know how much I want to actually say in detail about that. Let me try to at least give the moral idea. Well, maybe I actually want to say very little. So idea. This T side. Fully faithful implies R side. Fully faithful. Yeah, let me just say something a little bit cryptic here. So this is analogous to ideas in the proof of, let's say, the fact that the geometric Langlands conjecture with restricted variation implies the full geometric Langlands conjecture. If you stare at what's happening, this T is defined on this sort of small category, but it's fully faithful, and it turns out it preserves compacts, which automatically means it's fully faithful on the end completion of this. And then you analyze the difference between the end completion of this and sort of all of end code, and you see that there's actually not too much loss when you project from end code to this. Okay, so this is somehow completely formal, and I don't want to say too much about it because it's too much of a dose of abstract nonsense. The essential idea here, though, is the definition of this functor T and this spectral analog of the property of pseudo-identity star. Okay? But now let me come to this because this is really of key importance. So for GLN, I'm claiming we can actually prove the initial thing in this chain of implications. Okay? So again, this is somehow abstract nonsense. And so if you want to prove all of these things are fully faithful, you kind of are just reduced to this one calculation, right? And this might look not easy if you're optimistic or something. You just have to see where one thing goes. But this is actually really hard. And somehow, discussing this with Dennis Gatesworthy, he told me that in some sense, the analog of this in his setting is geometric Langlands. Like, for him, this is the essence of the whole problem. Oh, this board doesn't move. Okay, so now, assume G is G_n. How to compute inside I1 this paper sheet. Okay, so this seems rather hard to do from scratch. And the idea is instead try to understand the whole functor, say C psi composed of I1 over Schweik. I'll think of this as a functor from the bounded derived category of finitely generated QP representations towards coherent sheaves. And let me really put GLN in my notation so it's clear psychologically what group I'm looking at. Okay? Let me make another comment out loud, which is that earlier in the lecture I discussed this orthogonal decomposition into Eisenstein and custodal parts. And somehow the custodal part we deal with on its own. The hardest part is somehow the Eisenstein part. So somehow the more Eisenstein you are, the more difficult this becomes to understand. And so morally, if you can do it for the principal block for GLN, then you can do it for everything. Okay. And so in what I'm about to say, you may imagine I restricted to the principal block or something, because that's where it's most sort of contentful anyway. But let me not do that, at least on the board. Okay, so let me recall that there's another functor in town it's an explicit construction of a fully faithful embedding. Fancy S, dp finally generated QP. Let's compare sheaves on this stack of parameters. And this is by totally different means, and this is due to Bensby. Chen. And the nature of this construction is very much a generators and relations flavor. They observe that this breaks up into Bernstein blocks. Each Bernstein block has an explicit generator, right, which is even projective. And its endomorphism ring, somewhat by some Morita nonsense, right, modules over its endomorphism ring are equivalent to that block of this category. And so what they do is they write down for each block an explicit thing here whose endomorphism ring is the endomorphism ring here, and which has no self-x, it's outside degree 0, okay? And so, e.g., for instance, so let me give a flavor of this. So this functor, for example, and this one example is somehow the flavor of what it's doing in general. It sends the canonical generator for the principal block. So this is compactly supported Ihori invariant functions on G to, well, what they call the coherent Springer sheaf. So this is something that they write down on this side whose endomorphism ring is the Ihori Heck algebra. It has the same endomorphism ring as this by construction. But somehow, the hard part, once you guess what the definition of this should be, is to prove that its endomorphism ring is correct, and that's the essential content of their result. But the definition of this, at least using the notation I've set up, is very straightforward. So you take I's B spec, so B is the Borel, And then, well, the stack of L parameters for the torus has one distinguished component, which is very silly, right? Just unramified sort of L parameters into the torus. And that component just looks like T hat times BT hat, right? And on that component, you take the structure sheaf. So this is open and closed inside the stack of parameters of the torus. Okay, so this is by definition. Right, and what they prove is that endomorphisms of this identify with the Ewell-Gray algebra in degree 0 and vanish in all non-zero degrees. Okay, so it's not obvious that this sheaf has either of those properties. Questions about the flavor of that construction, at least?
Sorry, so just to clarify the embedding that that you were mentioning. So that does not use the Fargues-Scholze theory.
Absolutely not. It's completely by hand. It's by generators and relations. And it's even more so that you choose smart generators and then observe that there's no relations to consider. Yeah, so it's very much of an explicit nature. And they do something for more general groups too. For the principal block for any group, they write down an analogous functor.
And so the right-hand side, this coherent sheaves on, I mean, that's very explicit in this case, is that?
Well, it's the same stack on the right-hand side.
Yes.
I mean, I wouldn't call this sheaf explicit somehow. This formula for it is explicit, but if you try to prove things about it, it's actually extremely subtle. And they put a great deal of work into proving that, for instance, the endomorphism ring of this sheaf is Ewell-Gray algebra. Yeah. Okay. Other questions about this? And they also prove. And let me be very slightly sloppy, because I can certainly pass to incompletions on both sides and get something on the whole category on the left and have it map towards inco on the right. And they prove, once you do this, if you feed in the Whittaker representation, you get the structure sheaf. Okay, now maybe you can guess where I'm going with this. Here, GLN, C psi composed of phi1 lower shriek is the Benzvich and Helmholtz functor. And this is the only way I know how to prove that this takes the right value on the Whittaker sheaf. Right? It's to prove this more general statement that these actual functors match, and then they prove in their work that this particular functor takes the Whittaker sheaf to the structure sheaf. Okay? But they only do it once they've made some subtle analysis of this sheaf and its analogs for other Bernstein blocks. Okay? Exclamation point here. Okay. Let me say a few words about the idea here. The idea is actually already on the board. The idea is that the sheaves that they write down in their generator and relation style, if you stare at it, they are spectral Eisenstein series. And we are giving ourselves some compatibility of this with Eisenstein series. Okay? So the idea is to use explicit nature. Of S as the spectral Eisenstein series. Plus the compatibility of this C psi with Eisenstein series. There's one small key observation here, which is that these Bernstein generators tend to admit multiple presentations. So this one I wrote down as in this style, as equal invariant functions. But there's another rather different looking way of presenting it, which is as the parabolic induction from the Borel up to GLN of the universal unramified character. Okay. And under categorical Langlands for tori, it's extremely obvious that this universal unramified character matches with the structure sheet on this particular component, the stack of parameters for the torus T. And so once you realize that this is an automorphic Eisenstein series, and that they've matched it with a spectral Eisenstein series, and that we're giving ourselves compatibility of our functor with those two operations, then this theorem kind of proves itself. Okay? But again, I just want to emphasize that the whole reason that I needed this was to understand where this went. And in the end, you have to prove a bit more to know where this goes. Okay? And so for this, we really need GLN. Okay? It seems to be a very interesting question, which I think people are working on, of extending their work to other groups. Okay? And it gets harder because the sort of Hecke algebras that show up are no longer just these very simple Euclidean Hecke algebras, right? You have these more general sort of twisted affine Hecke algebras and stuff like that. So if I understand correctly from talking to David Helm, there's sort of work in progress on doing this, which hopefully would lead to generalizations of this step to other groups. And that's the end of the discussion of step 3 in this strategy, that this right adjoint functor is fully faithful. Okay. Any questions about what's happened so far?
How much time do you need for step 4?
5 minutes, because I don't want to go into details. I want to give the essential idea, which is a very soft idea. And it actually brings us back to a question you asked yesterday, which was exactly the right question.
What question?
You pointed out that we had this semi-orthogonal decomposition of G sub on G. You asked whether it's easier to do a similar thing on the spectral side. It turns out it's harder, but that's exactly what one needs. And so for step 4, to show this L psi is conservative. And because we know that L and R both preserve compact objects, it would certainly be enough just to know that this is true on compact objects. And I should also say that the morally correct approach is not available. The morally correct approach is this conjecture I made in my lecture at the conference last week, that these Whittaker coefficient functors form a conservative family. So this would be the analog of the theorem of Feynman and Raskin. Right, that is functor C size conservative on compacts. That's exactly what they prove in the D module setting. This is not available to us, unfortunately. So not available. So what we do instead the alternative idea, let me just capture it in a lemma, and I'll explain why this would be relevant. So if I have a functor between some categories which are semi-orthogonally decomposed, semi-orthogonally decomposed categories, which respects the decomposition. Such that L restricted to each piece of the decomposition C is conservative. This respecting the decomposition, and such that L in each piece of the source category is conservative, then L is conservative. Okay, and the analog of this with conservative replaced by fully faithful is not true, but with the word conservative it is true. Now, I really want to be vague here, but let me just explain the principle of how we want to apply this. So I want to apply this, taking advantage of two things. And so one is that this L psi composed of I1 lower Schriek, this is this Bensby-Chenholm-Nadler functor, as by what I've already discussed. This is conservative, in fact, it's even fully faithful, right? And remember, the semi-orthogonal decomposition comes by sort of these other functors where you vary B. And this will be conservative by induction on levies using this IB sharp thing. I didn't say this explicitly, but this is an important thing. This is a fragment of an Eisenstein series. Okay, and so this reduces you to the question exactly that Professor Grünfeld asked. Can you write down a semi-orthogonal decomposition of coherent sheaves on the parameter stack, which matches the given one on sheaves on Fun G? Okay, so that's the goal. And let me just write that on the board and then I will stop. So thus, it suffices to decompose this semi-orthogonally in a way that matches decomposition of sheaves and bungee. And let me be a little bit careful about the status of this, because again, I told you we're not completely done with everything. So we have candidates, precise candidates for the pieces of this decomposition. And for GL2, we've checked that they assemble semi-orthogonally. So this is okay for GL2. And we have candidate, which if you believe the categorical conjecture, there's only one candidate that's possible. Somehow this one that we have is the only one that's possible. We have candidate in general. We're still checking the details of the proof that they actually assemble in the correct way. So I don't want to claim that we've fully established this yet. Okay, but that's the strategy. I think I will stop here. Yeah, let me stop.
Thank you.
Yeah, you might also ask yourself, what is any of this good for? And I hope to answer that on Friday.
Can I ask you a question?
Yeah.
So you said, could you say something about the C side being compatible with Eisenstein series that was used as
In this proof?
Yes.
Or like the step 3, or
sorry,
is this from Zoom or from?
sorry, this is from me.
Okay.
I thought you explained that one of the things that you were using was C side being compatible with Eisenstein series.
Yeah, that's right. That's right.
Could you say something about what goes into that?
Can I explain something about what goes into that, like proving that, or
Yeah.
where that's used?
Or sorry, what? Could you explain something on the proof of that?
Ah,
Proving that.
not really. That's like its own really involved project.
Oh.
It's proved in GLC 3, the third of these 5 papers, and there is a sort of a template for us to follow, but this is its own sort of sprawling thing. And so the talk I gave last week was one component of that project, actually. Yeah, so you sort of try to cross your heart and faithfully redo everything that they've done to prove that in their setting, in our setting. So we have to develop all kinds of factorization geometry over our version of random space and stuff like this. Yeah, but I'm hopeful at the end of the day it'll work. But I'm trying to be clear that it's still a hypothesis somehow throughout this. Other questions?
say something about this candidate then?
Yes. Let me try to say a little bit out loud, and then I'm not sure what I'll actually write on the board. So this, the hardest part is actually figuring out what should correspond on the coherent side to the things that live on these open points in Bun-G on the morphic side. Okay? Because once you've done that, you realize that sort of this GB, this B will be an open point in Bun for an explicit levy, and then this is an Eisenstein series. And so when you translate that, you see that you have some spectral, this should translate into some spectral Eisenstein series applied to the coherent analog of a sheaf that lives on some open point. Okay? So the real heart of it is what does this condition of living on an open point translate into? Okay, and this I have a good answer for it. So definition. F in co for a sheaf is basic. The definition is actually quite clean. This spectral constant term, this chi-graded spectral constant term with F is 0 for all pairs K chi. But recall chi is a character of the center of the dual group of the levy, right? Let's say P a proper parabolic. And I need that chi is strictly P dominant. So one way to think about what I mean by this is this chi gives me a character of the center of this levy. Characters of the center of this levy are the same thing as basic elements in B of M. A basic element in B of M will have a Newton point, which will be a co-character into T, right? And you want that one parameter subgroup strictly contracts the unipotent radical of P to the identity, okay? If you believe the categorical conjecture, it's a theorem that these are exactly the sheaves which will match things that are Schriek extended from open points in Bun-G. So these are the sheaves that live on the basic strata of Bun-G. Okay? And then the idea is that these pieces here should come by applying suitable spectral Eisenstein series to basic sheaves, but on parameter stacks for levies. Okay? But this is a subtle condition to work with. So for instance, we proved, actually last week, we finally managed to prove, for instance, that this sheaf I wrote S, this coherent Springer sheaf S, we proved that this is basic in this technical sense. But it's not an obvious calculation. Okay, so this implies, co RG basic matches. Sheaves and Bun-G. Which are Schriek extended. Excuse me. From open points. Okay. I think maybe that's enough for me to say about that part of the story. Does this sort of answer your question? Yeah? Okay.
And how do you distinguish like those B's in the basic strata? You like decompose it by like CG hat?
Yeah. This is still graded by characters of the center of G hat. Yeah, and so you can speak about a sheaf here being basic and graded for one character, and that will pin down exactly the things that come from the matching basic B. Exactly. So there's an even more refined version. This is a key step.
Are there other questions? Let us thank
Yeah, thank you.